Good afternoon, everybody. Welcome to another exciting time of organic chemistry, Chem 170, with your host, me, Dr. White. I hope you all saw the email and the announcement. I'm postponing test number 1 by 1 week. Ooh, stop. Anyways, it's obnoxious Monday. By 1 week, and a week from this Wednesday will be test number 1. And by this Wednesday, I'll put out an announcement and email giving you a breakdown on test number 1, how many pages, how many problems, how many points, and also, I think that's about it. What it's not, well, I should say, what areas it will cover. It will cover chapter 2, 3, and 4. I'll finish up 4 today. That's hydrocarbons, alkanes, cycloalkanes, alkenes, double bonds, alkynes, triple bonds, and aromatic compound. And that will be test number 1. Now, I should point out a couple of important things about my test. One, if I haven't told you, I teach by the golden rule of teaching. My golden rule of teaching is I don't do to my students what I didn't like done to me. When I was a student, yes, I still remember those days. And I did not like when a teacher would write a test and only a few people, the smartest people in the class, would finish. That's not fair. My test, if you studied and done the practice problems, hint, it should take you about 40 minutes. I give you a lot more time, but you should. Also, every question on my test, I've covered the concept for that question in lecture at least twice, usually a lot more times than twice, but I guarantee at least twice I've covered it in lecture. I don't like going, oh, I talked about it, I'm done. It's your turn to learn how to do it. No, I'm going to cover it thoroughly. And you'll learn more about it when I talk about Wednesday. All right, let's get to work. First of all, are there any questions about anything? All right, next, don't forget tonight, I have my office hour from 5 to 6:15. If you need any help, come on by. And don't forget, the first slab is due this Wednesday. I know 4 of you have handed it in already. I wait until the deadline when it's supposed to be due before I grade them. Usually I'll have them graded within about 48 hours after that and post it in D2L. Normally, if we're face-to-face, you'd hand it in this Wednesday and next Wednesday I'd hand them back to you. Well, that's not going to happen because we're not face-to-face. All right, let's get going. All right, thumbs up, people. My Zoom just burped. Thank you, Megan. All right, we're talking about aromatic compounds, really benzene and derivatives of benzene, things on a ring with 3 double bonds that are conjugated. Now, when you try and react benzene, like you would if it were double bonds, you don't get anything reacting or barely reacts. Why is this so? Well, this is due to resonance stabilization and the kind of reactions benzene and aromatic compounds undergo are electrophilic aromatic substitution. Well, aromatic means we're dealing with an aromatic ring. When I tell you, you're going to learn some really neat vocabulary this semester that you can impress your friends and loved ones with. Now, what's electrophile? Well, phile means lover. Electro, that comes from electron. And what charge is there on an electron? A negative charge, or just think of it as electrons. So electrophilic means it's something that's looking for negative charge. And if I back up, which I will, because I can, any day now. Here's the benzene ring with its pi electrons to form double bonds, but they really are all holding hands. And if I were electrophile, electron loving, file or electron file lover. And if I see these pi electrons right here, I'm going nuts. Yes, I want that. So I attack it. Oh, did I tell you organic chemists are very violent? We use terms, actually we do, instead of it bonds to it, we say it attacks it. So electrophilic aromatic substitution or substitution reactions, due to resin stability, you're not going to break the double bonds in a benzene ring. It doesn't want to. It makes it less stable, and that's not going to happen easily. But remember, on each carbon in benzene, I rarely do this, so write this down in your diary. Dr. What? No, you don't have to. Put hydrogens. What aromatic compounds, and for this class will be benzene, you replace one of the hydrogens with something else, a substitution reaction. And these are chemical reactions where the hydrogen atom on an aromatic compound is substituted with another atom or group of atoms. All right, let's look at our first aromatic, electrophilic aromatic substitution reactions. Now, I'll never ask you names, but I'll use them. And that first one is halogenation. And halogenation, you start with benzene ring. Remember, X is our halogens. X2 means halogen gas. But unlike a double bond, you also need a catalyst, ferric trihalide, FeX3. Now, in real life, and since I've worked in the real chemical world for many decades, for this reaction, you only see it for chlorine and bromine. I don't know about iodine or fluorine. I've just never seen it. So what you get, you replace one of the hydrogens here with the halogen. You get this back as the catalyst, and H and 1X, and you get HX like HCl, but this is inorganic. It's an acid. Now, organic chemists are very, what would be the right term? Really are discriminatory, just believe in discrimination. We don't like inorganic, or more importantly, we just think about organic chemistry and organic molecules. So my test for this type of problem, I'd ask, give the organic product or products. You want to put HX down there and it helps you? By all means do. If you don't, don't. I don't. So let's look at this reaction. Now, one thing I do have to teach you, which I don't think I've mentioned this before. Generally in inorganic chemistry, you'll see a chemical reaction, A plus B makes C. Now, organic chemists are lazy, and sometimes we'll write it this way, but a lot of times, and this is an example, we'll do this. Anything above or below the arrow, A reacts with A, and if there's something below with B, and if there's something below the arrow, we'd have that too, to make C. So we can write these chemical reactions one of two ways. Now, here I'm doing the same thing. If I look at this, what do I have that's different? Oh, a benzene ring. What's bromine? It's a halogen. Oh, ferric trihalide, and I wrote that wrong, sorry. Is ferric trihalide. Remember, X can be chlorine or bromine, and you replace one of the hydrogens with a halogen. And for those of you who came in late, hi, I should better tell you, you should have gotten an email from me, Dr. White, that I'm postponing test number one. Oh, stop. Test number one. By the way, today's obnoxious Monday. Oh, no, it's Monday the 13th. Oh, that's only on Friday. But I've had a lucky Friday the 13th. But anyways, test number one will be postponed by 1 week. And this Wednesday, by Wednesday, I'll have an announcement, email sent out describing test number one. All right, so what do we have? Benzene ring, halogen, gas, ferric trihalide, replace one of the hydrogens with a halogen. And what's the halogen? Bromine. You can put it on any carbon, it means the same. Now, watch closely. Common mistake I see on test number one, a student will write this. And I'll give them 0 points. Yes, 0. And the student will argue, well, can I get partial credit? I said, no, that's like bromocyclohexane. This is bromobenzene. Those are as different as my ear and nose on my face to an organic chemist. This is wrong. Don't forget, put the bonds in there. Now it's bromobenzene, or if you like, which I think the bonds are cooler, but you can also use the delocalized. You have to put something inside the ring. Otherwise, it's wrong. And as you know, Dr. White likes to share the fun. So oh no, I'm having a bad ring drawing day. Sorry. It's your turn. What would be the organic product or products? And I'd have written here. And when I put an S in brackets, that means there could be one product, or sometimes later in the semester, more than one product. Your turn to have fun. And for those of you who finished early, please be patient. I try and give everybody time to finish. And the thumbs up people, thank you. All right, looks like everybody's done, so I gave you enough time. Let's look at this. What do we see that's different? What's not a carbon-carbon single bond or carbon or hydrogen? Well, there's a lot of double bonds in this ring, and it's benzene. And I have chlorine gas, X2, and I have a catalyst, ferric trihalide. Remember, X for this reaction is chlorine or bromine. And what happens, you replace one of the hydrogens with a halogen. In this case, what's the halogen? X, chlorine. So don't forget to put the double bonds or circle on the side. And that makes it benzene, and we get chlorobenzene. And that's how you do it. Now, a couple things I want to talk about on all of my tests. When I ask, give the organic product or product, there will always be something happening. You'll always have a chemical reaction. The term no reaction will never, ever, ever be correct on a, I'm going to go full screen on this. When I ask, give the organic product or products for a reaction, the answer, no reaction, will never, ever be valid for my test or final. When I was a student, sometimes the instructor would try and trick us in organic chemistry and put something down, and the answer would be no reaction. I'd get upset. Well, if you ask me to put down products, there should be a chemical reaction. So on my test, there always is. Now, let's look at something important about the reaction I just showed you. Halogenation. Let me get to my whiteboard. what happens if there's something on that ring I'll call Z. For some reason, eons ago, aromatic organic chemists put Z instead of something else, and I don't, probably because it's not used as an element symbol. Well, now we've got, if we just think about it without that, and for what I'm talking about now, I will be turning the switch. Will this be on the test? Off. Well, the general reaction, we replace one of the hydrogens with a halogen. Now, if we look at the example I just wrote, if I can get it back down, there we go. No. Where will I replace it? Well, I can replace it here, 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 and here. This is the ortho on either side. This would be the meta position, and this would be the pair. Now, depending on what Z is, there's two types of directors. Again, switch is off right now. And the two type are ortho pair director and meta director. And depending what Z is, you'll either get a compound with a halogen at the para ortho and another one at para. You get two products, or you just get one at meta. Now, I can spend the next couple of hours teaching you different types of directors. Guess what? None of you are going to be organic chemists. I'd rather spend time later in the semester instead of a couple hours now on what Z will do on things like fats and oils, carbohydrates, proteins, things that you might find more useful. So I will not cover directors in this class in the lecture for a question on the test, but I still want to give you that experience. So not this week, but I think next week it is, I'll have a lab where we deal with directors, or the one or the week after. And then you'll learn about it in lab. But remember, anything I cover in a lab will never be on an hourly exam. You can all say, yay, Dr. White, thank you. But anyways, lab should be fun. That keeps them fun. So what does this mean? If I'm not going to cover directors, the only two reactions I can ask you on a test is this one right here, or this one right here. And we're done with halogenation because I'm not going to cover directors in the class. All right, let's move on to the next reaction. And this is called nitration. If you take benzene and react it with nitric acid, HNO3 is nitric acid, and this is sulfuric acid. On a benzene ring, you replace one of the hydrogens with a nitro group, and that's called nitration. And that's quite important in many things. And that's one way, and I will not recommend you ever try this at home, at making trinitrotoluene 2,4,6 by nitrating something. But why the nitric acid? Why the sulfuric acid? Unfortunately, this semester, I only have one semester. in organic chemistry, when we show things, what are happening stepwise, we call that the mechanism. In 2 semester, you put mechanism problems on the test. In this class, I never will. But I thought I'd just show you something to help you out to understand what's going on here in nitration. Unfortunately, we'll have a lab, but in face-to-face we do this, and you nitrate something. That's when I teach you about directors. Don't forget the bonds inside the benzene ring. And that's the only reaction I can ask you on test number 1. But let me just show you something. Here's nitric acid. This will never be on a test, but it might help you understand this reaction. Now, sulfuric acid is an acid. An acid is a proton donor, and a lot of times for sulfuric acid, we'll just put down H+. This reacts because the non-bonding electrons of the oxygen attract the hydrogen H+ to form this. And now this has a charge associated with it. Again, this won't be on a test, but you might find this useful. Now, if I look at that molecule, and if we're in a classroom, I'd put my hand over the screen, but since we're not, I'll use colorful pen. If we look right here, anybody see something familiar? Let's see, 2 hydrogens, 1 oxygen, 2 hydrogens, 1 oxygen, H2O. Oh, it's water. And whenever you form something in a molecule that's a stable leaving group, meaning a stable molecule, if it left, guess what? It does. And immediately it says, well, as soon as you form this, the water says, I'm out of here. And the minus H2O means it's out of here. What's left behind? This. This is called the nitronium ion. It's got a positive charge, and it wants electrons in the worst way. Where can I find electrons? Here, and that's why you put on an NO2 group. Now, students, a common mistake on test number 1, first of all, they forget the bonds. Don't forget the bonds in there, and then they'll do this. And I'll mark it wrong because no such thing exists. And that's why I wanted to show you this. When you mix nitric and sulfuric acid, this is called the electrophile. It's looking for, and that's NO2 plus, called the nitronium ion, cation. And that's what attacks and bonds to the ring. This is wrong. And guess what? That's the only reaction I can put on a test number 1 because I'm not going to teach you directors. So on a test, if I asked you the following, what's the product or product? Well, that's the general reaction too. I'll write it underneath. And I'll ask for what's the organic product. You put a nitro group on there, replace. So the answer here is surprise, surprise. Don't forget the bonds inside. I had a student once lost 10 points out of 100 because she forgot to put those bonds in there, and that was cyclohexane. She was not a happy camper when she got the test back, because she should have gotten 10 more points and gotten a good strong A instead of a B. But anyways, that's nitration. Now, another reaction, which is the only one I can show you, is you take sulfur dioxide, sulfur trioxide, and sulfuric acid and react with benzene. You put on a sulfonic acid group. Don't forget the H here. And sulfur trioxide reacts with the H plus to do a similar type electrophile. Now, one of the questions I'll be reminding you to ask more and more of is, why am I learning this stuff? Well, the obvious answer is you want to get a good grade in my class so you can get into some school or program. Well, why do they want you to learn this? Well, it turns out being able to sulfonate, that's what this reaction does. This group can be converted, and I'll show you later in the semester, to something else. And this reaction is used to make, are you ready for this? All the detergents we use to make our clothes clean, laundry detergent. This is one important reaction to make the key ingredient in all laundry detergents. 90% of them, it's called linear alkyl sulfonates. And I'll teach you later in the semester about that, week 15 or so. But if we didn't have this reaction, you wouldn't be using your laundry detergent you have today. You'd be using something they used back in the 1800s, early 1900s, which is not as good as what we normally do. By the way, and this is my personal preference, partly because my mother used it, and also because I know it's a very good product, I use all. Tide is also, they're all similar, but I like all. It's been good to me. I've been good to it. I buy it. All right, let's move on. Well, let me have you do one reaction. Give the organic reaction products or product for the following. Your turn. And remember, these reactions are used as the building blocks to ways to make molecules that you use in your daily life, like your laundry detergent. All right, let's do it. What do we have? Sulfur trioxide, sulfuric acid, a benzene ring. What's the general reaction? Uh-oh, I'm going to rewrite this reaction twice. And we put on a sulfonic acid. Don't forget the bonds or circle in the ring. And that's what you get. Students forget that H, and I mark it wrong, 0, because SO3 doesn't exist. It's sulfonic, SO3H. And therefore, the answer up here is the same thing. Don't forget the bonds inside, and don't forget the H. This is a sulfonic acid group. And that's the only reaction I can ask you on test number 1, because I'm not going to talk about directors.
I have a quick question.
I do slow questions too. Hold on, let me do this. Go for it.
Where is the H coming from on like the product side of the reaction? Like when it gets added onto the SO3? Is it from the?
Yep, this is H plus.
Oh, okay, okay.
Here's where I always mess up. I think there's like this. And this becomes okay. And that's, notice, SO3H plus, and this is what attacks the benzene ring. I'll never ask that on a test, but if it helps you learn, Gang Gazette. That's a good thing. All right.
That makes sense. Thank you.
You're welcome. All questions are good questions. And now let's talk about the last reaction in aromatic compounds. Now, one thing I need to teach you, first of all, is in the last 20 years, it's died off, but for many decades, if you came up with a very important reaction you discovered, it was named after you. And this reaction happened to be discovered by two great organic chemists, Friedel and Crafts. And it's called Friedel-Crafts Alkylation. And this is a very important reaction in the fact that you can do something that's very rare and very good in organic chemistry. You can make a carbon-carbon single bond. Now, Friedel-Crafts involves reacting a benzene ring. Now, R means anything with carbon hydrogens, X is a halogen, and you need aluminum trihalide. Now, in my experience, X is only chlorine or bromine, mainly chlorine. I think a lot of that is economics. And what happens is the carbon's R group is bonded to the benzene ring, and you make that special thing, a carbon-carbon single bond. Now, let's talk about what R means. R means anything with carbons and hydrogens, just like X, Y, and Z in math is any number. And R can have 1 carbon, 2, 5, 10, 100, 1,000,000. I've never seen it with 1,000,000, but it could theoretically. And it could be on a ring and all sorts of things. So let's have some fun with Friedel-Crafts alkylation. And the question would be, now you form HX, which is an acid, unless you're doing this in the lab, actually hands-on or in a chemical plant, we just ignore that. When I say give, that means draw. Let me ask a question real quick before I continue on. Now, the polling which I have will say, are you done? And what I really mean to ask is, I'm not going to waste the time writing a special question. I just do once. Instead of are you done, can you read cursive handwriting? Yes or no? Well, it looks like everybody can. It's interesting. My morning general chemistry at the other school, about a third of the students couldn't. So in the future, I can write here. By the way, a good question is when I'm writing something, what did you just write there? I can't make it out. Could you translate that for me? But let's look at the following reaction. I'll do this one. You know I'm going to share with you. Oh, I've got a benzene ring. Remember, above and below, oh, I've got a catalyst, aluminum trihalide. Remember, X can be chlorine or bromine. And I'll never trick you by putting iodine or fluorine there. That's not right. I don't do that. Now, if we look up here, look for what's different. Always in an organic molecule. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. And, ooh, look, a chlorine on a carbon. And we call that Rx. Now, what's my R group in this case? It's these three carbons. Now, one of the important things is, first of all, Friedel-Crafts alkylation. Don't forget the lines in the center. I replace 1.5 hydrogens on the benzene with the R group. Now, listen carefully. The bond from the benzene ring to the R group goes on the carbon that has the halogen bonded to it. The bond from the benzene ring to the R group is to the carbon in Rx that has the halogen bonded to it. Now, for my general reaction, I'll have my benzene ring. Don't forget the lines or circle. And then I have 3 carbons. Now, something I haven't mentioned a lot, but I'm starting to. Do you break carbon-carbon single bonds? No. So I have my R group, 3 carbons. Which carbon has the halogen? The N carbon. So those 3 carbons. And remember, there's 4 bonds to carbon, 4 I can put in, and we don't show hydrogens on a ring, and that's my product. And you've done something very special, very rare. You made a carbon-carbon single bond right there. I haven't mentioned it. Maybe I did, but I'll mention it now. I don't think I did. I know in this class, a number of years ago, one student counted, and I think I'm going to be teaching you about 52 general reactions, give or take one. I know about 450, 500. I've lost count. And all the reactions I know in organic chemistry, there's only about 15 or 20 that you can make carbon-carbon single bonds. Very special, very rare, very good to do. And this is one of them. All right. Well, I better let you try it. Your turn. I see one person done. Don't forget when you're done, give me a thumbs up. Oh, I just thought something. Do all of you have a thumb? Maybe I should do, give me, never mind. I never thought of that, but luckily I haven't come across that problem. All right, let's do this. What's different? Ooh, a benzene ring. That's different. Remember, what's not a carbon-carbon single bond or carbon or hydrogen atom to get your attention like that. And if I look up here, what do we have? Carbon, hydrogen, ooh, halogen, bromine on a carbon. And how do we show that? Rx. And I have a catalyst, aluminum tribromide. Remember, X can be chlorine or bromine. And I replace one of the hydrogens with my R group. Remember, the carbon with the halogen is the carbon my benzene ring is bonded to. So what's my R group? This. And what carbon has the halogen? The center carbon. Do we break carbon-carbon single bonds? No. So I'm going to have my benzene ring. Don't forget to put the lines in there. You don't want to be like that one student who lost 10 points by forgetting to do that. And then I have 3 carbons. Which carbon has the halogen? The center one. And there are 4 bonds to carbon. And that's how you do it. And that's Friedel. Oh, let's do one more. These are fun. Now, sometimes when R is real big, you don't put it above the arrow. And it's your turn to have fun. And if you finish early, please be patient. I try and give everybody time to finish. 2 people done. If you're not done, take your time. And don't forget, it's still always true. There's no such thing as a dumb question in my class. All right, I think everybody's done. Let's take a look at this. What's different? Close that ring up. Oh, I've got a benzene ring. When you look at a molecule, you look for what's not a carbon-carbon single bond or what's not carbon or hydrogen atoms. If we look at this one, well, I got a ring. This is carbon-carbon single bonds. Oh, look, I've got a halogen on a ring. In this case, chlorine. I'll call that Rx. And I have an aluminum trihalide catalyst. Remember, X can be chlorine or bromine. And what happens? You replace one of the hydrogens on the benzene ring. Don't forget the double bonds with an R group. And the carbon with the halogen is the carbon bonded to my R group in my product. What's R? A cyclopentane ring. It doesn't matter which carbon you put it on. Uh-oh, my Italian roots, which I don't have any, it's like the Leaning Tower of Pisa. Anyways, that would be cyclopentyl benzene. And another way I could have drawn it would be that way, and all I've done is rotate it 60 degrees. And either way, you have a 5-membered ring attached to a benzene ring. And that's how you do it. Now, having worked in the chemical industry for many decades, being a senior research and development manager, having been hired and also hired people, you will never hire a person, organic chemist, bachelor's, master's, or PhD. Oh, we want you to find out if I react this and this, what do you get? No, that won't ever happen. I can't ever remember that happening. What you will be asked to do is, how do you make something? And at my level, is how do you make something that does a certain thing at a certain price in our existing equipment. Then it gets challenging and fun. And that's called synthesis. Now, coming from industry, I'll usually say starting material or materials for the following. And this is when organic chemistry is fun. And the question would be something like this. And now if we're looking at this, and I'll make it easier, when I was a student, my instructor didn't give question marks. So how do you make that? Well, you look at the product and say, what's different? Well, I got a benzene ring and substituted, it's got carbons on it. And I'm reacting it with, a catalyst, aluminum trihalide. And what do I react to do that? A benzene ring. Here's where you have to know your general reactions, plus an alkyl halide. Now, what's R? Well, in this case, ethyl group. So therefore, one of these question marks would be a benzene ring. And what's my R? Ethyl. The carbon with bonded to my ring here is the carbon that will have the halogen. What's that? Chlorine. And that's the answer. If you react those two together, you will get that molecule. Now, this is a much harder problem to do than give the product or products. So on test one, I only have one, what I call synthesis problem. Give the starting material or materials. Why? Because, at least as of today, the Supreme Court has outlawed cruel and unusual punishment to students, and having more than one synthesis on the first test is definitely cruel and unusual punishment. When I was an undergrad, a lot of our points were those type, but I was a chem major and you were taking organic for chem majors, and you expect to learn that. For you on test one, I will just put one problem. And if I look at the time, I think we're about ready for a break in about 30 seconds. So I'm going to start our break now, come back at 1:55, and we'll continue. I'll see you in 5. I'm going to get up and stretch. That was weak. That's better. It's time to get started again. All right, is everybody back? All right, let's get going. Now, I was showing you synthesis problem, and that's where you're given the product and you have to find the starting materials, also known as reactant. And I gave you an example here, so I better let you try one. So you can have some fun too. This is the best part of organic chemistry, but don't forget, I'm a synthetic organic chemist, which means this is the fun part for me, always has been. So the question would be, if I have two question marks, that means there's two starting materials. That's my special gift to you. Don't tell anybody I'm being nice or ruin my image around here. Shh. All right, one person's done, but this isn't a race. Everybody take your time, but give me a thumbs up when you're done. Well, there's three. Take your time. I think everybody's done. So let's get to work. And if I'm trying to find out what are the starting materials, I look here, ooh, aluminum trihalide. X can be chlorine or bromine. And then I have, ooh, a benzene ring. That's different. And it's got stuff on it. Stuff on it doesn't sound scientific. It has a substituent on it, which I'll call R, carbons and hydrogens. And we know this is a alkylation of a benzene ring. Alkylation comes from the word for putting an alkyl group on a benzene ring, which I'll never ask on test. And this is it. What's my R group? These four carbons. Now, my first question mark is a benzene ring. Now, the carbon with the halogen bonded to it is the carbon that is bonded to the benzene ring, which makes this carbon right here the carbon that will have the halogen, in this case, bromine. And do you break carbon-carbon single bonds? No. So if I end up with four carbons in my R group, I better start out with four carbons. The N carbon, in this case, has the halogen, which is bromine. And I know there's four bonds to carbon. I can put in my hydrogens. And that's how you have fun with synthesis. Now, on test number one, I can pick any of the general reactions that I gave to you. By the way, this is a symbol I started, I don't know, in college, maybe high school. That's the end of that thought and start something new. Let's do another synthesis, same thing. I'll do this one first. what would you react with chlorine gas to make that molecule? How do you do that? Well, you look at this molecule and say, what's different? What's not a carbon-carbon single bond? What's not carbon or hydrogen? Get your attention like that. And oh, look, not only one, but two chlorines on adjacent carbons, adjacent meaning next to each other. And chlorine gas, Cl2 is a halogen. And for this reaction, the halogens can be chlorine, bromine, fluorine, or iodine. And what do you start with? A double bond. And the two carbons of the double bond become the two carbons with the halogen. Therefore, do you break carbon-carbon single bonds? No, other than combustion, which we're not burning anything here. Therefore, if I end up with 4 carbons, I better start with 4 carbons, because am I putting any carbons there? No. Which 2 carbons have the halogen? These 2. Therefore, they have to be the 2 carbons in double bond. And now I know there's 4 bonds to carbon, so I can put in my hydrogens. If I take this molecule, react it with chlorine gas, I will get what I'm trying to get. That's the fun part. Sort of like chess in reverse, or I don't know if you've ever talked to someone or played chess, but the great chess masters can think 10, 15 moves ahead. And this is like that, but in reverse. All right, let me have you have some fun. It's your turn.
I have a question.
I do questions.
Is
Calvin.
the carbon at the end in the product that's
I made
bonded
a
to the bromine?
mistake. Hold on. Bad Dr. White. I got an extra hydrogen. Remember, it's your responsibility, which you just said. Thank you very much. And that will happen the rest of the semester. Thank you, Calvin.
Yeah, thank you.
No, thank you. As soon as you're done, I'll do a quick Dr. White story from when I was an undergraduate. What you just did reminded me of something, Calvin. And when you're done, give me a thumbs up. Thank you. Psst, organic chemistry isn't that painful. It might even be fun. Bet you never thought you'd be smiling in my class or organic chemistry class. All right, I think everybody's done. I better get to work. If we look at this molecule, what we're trying to make, What's different? Ooh, halogen here, halogen here. I'd carbons with adjacent halogen. Look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. And those halogens stick out like a red flashing light from a fire truck. And we have halogen gas here. Remember, X can be for this reaction, fluorine, chlorine, bromine, or iodine. And what do you start with? A double bond. And the two carbons with the halogen are the two carbons of the double bond. Now, am I adding any carbons here? No. So I end up with 1, 2, 3, 4, 5 carbons. I better start with 1, 2, 3, 4, 5 carbons. And which carbons have the halogen? These two, which are these two. Therefore, there's going to be a double bond there. Keep an eye on me. I made a mistake once today. Make sure I put the right number of hydrogens. And if you take this molecule and react it with bromine, you'll make that molecule. And that's how you do it. Now, there's another one I want to show you, but since Calvin was nice enough, and I really mean to thank you, to point out an error I make, and remember, it's your solemn responsibility. If I put down the wrong number of hydrogens or any other error, let me know. And the memory I just brought back, which I'll share with you, when I was undergrad at IIT, Illinois Institute of Technology, I was taking, I think it was second semester calculus or first, I forgot. And it's a lecture hall. IIT is small, but first year, all the physical science majors, chemistry majors, and all the engineering majors took the same, when I went there, the same curriculum. Anyways, we're in this lecture hall, about 250 people, got students, and the instructor was the old lecture hall. So have you ever seen it with the 3 boards that slide up and down? And there are 3 sets, so 9 boards. It was a lot of board space. And he said, today's lecture, I'm going to show you how to use calculus to calculate this volume of some shape like a sphere, which he said, and here's the actual formula that's been figured out. And he goes and starts filling up all those boards, takes about 35, 40 minutes out of a 50-minute lecture, and he comes up with the wrong answer. And he's looking at the board and going like, what did I do wrong? Anybody see? And he goes on like that for 5 minutes and nobody could find it. And finally he said, stop. The very first board he pulls down, the first thing he wrote down, that's wrong. Every one of you should have pointed out it was wrong. I did this on purpose. And the whole purpose of that lecture was, just because I have a PhD, in his case in math, I'm your teacher. If I write something wrong on the board, it's wrong and you should point it out. And that was decades ago, and I can close my eyes. I can still picture that lecture like it just happened 5 minutes ago. And that was a very important thing he taught us. Just because you have credentials in whatever doesn't mean you can't make a mistake. All right, let's have some more fun with synthesis. Now I'm going to give you one, try on your own, but I will do the following. I'll give you the general reaction, but on a test, I won't. And why don't you try this one on your own? What would be the starting material for the following reaction? And on test, I won't do this, but today I will give you the general reaction you should be able to pick up. Don't forget, write them down 5 times and say them, and that'll help keep them fresh in your memory. I see one thumbs up, but the rest of you take your time. And the thumbs up are starting to come in. All right, looks like everybody's done. Let's do it. If we look at this molecule, what's different? A halogen on a carbon. Well, how do I put one on adjacent carbon, one next door, I have a hydrogen, which is this, HX. And what do you start with? A double bond. Remember, it follows Markov-Nikolson rule. Now, do you break carbon-carbon single bonds? No. How are we adding carbons? No. So I'm going to have 4 carbons across. I'm going to still have my 2 methyl groups. Now, here's something you should know. One carbon of the double bond that here we end up with is 1 carbon of the double bond has the halogen. The other one has a hydrogen, and that only exists like this. And now I'll put in now, watch closely. Don't forget this one. Watch closely. This is wrong. How many of you, don't raise your hand, just sort of look sheepish. I don't know what that means. How many of you tried this one? If you did, let me show you why. Immediately, you should know it's wrong. We look at this carbon. First of all, let me write it. How many bonds to the carbon with the red dot? Let's count. 1, 2, 3, 4, 5. It has 5 bonds to carbon. No way, never. You find a way to do that and let me know, and we'll be rich beyond my wildest dreams, which goes beyond my own Lamborghini and Ferrari, goes beyond my own fighter jets to play with, and goes beyond my own islands, more than one, in the South Pacific. It can't happen, and this is the right answer. So remember, 4 bonds to carbon, and this is synthesis. And any of the general reactions I taught you for chapter test number 1 material, chapters 2, 3, and 4 are fair game to put on test number 1, but only have 1 question. Any more would be cruel, unusual punishment, which is outlawed by the Supreme Court of the United States, at least today. Who knows about tomorrow? Oh, wait. Keep politics out of my class. All right, any questions on this? Now, I'm going to turn the switch off. Will this be on a test? I'd still like to cover it because it's stuff in our daily life. Now, the area deals with polycyclic aromatic hydrocarbon. Ooh, what does that mean? Well, the word poly means many. And this means rings. aromatic 4n plus 2 pi electrons conjugated in hydrocarbons as carbon hydrogen atoms. And these are aromatic hydrocarbons with more than one ring. Now, I haven't talked about it, but you can also have this with cycloalkanes, which is what we call fused rings. But remember, it switches off. But the simplest one I can think of is this molecule right here. Notice we have two 6-membered rings. I could call this one, that two. They share the same carbons, and they have alternating double, single, double, single, double, single, double, single. So this is aromatic, and this is called naphthalene. And for those of you old enough to remember, I can. I don't think people do it anymore. How many of you have ever smelled them or seen a mothball? No. Back when I was a kid, I don't know why it's not, moths love wool. If you had wool sweaters or whatever, they would somehow get into your house and eat them. Don't ask me how or why. And people found that this compound, naphthalene, which is a white solid at room temperature, can be molded into these little balls about the size of a marble. And I think I just did. How many of you have ever played marbles? Oh, wait. I see one. I was a marble champion in 8th grade, and when I was 8 or 9 years old, my school. But that's another story, another day. Well, anyways, they're about this big, about an inch, and you throw them in the drawer with your wool sweaters or other things, or you have a closet and you throw them in the bottom, and the moths don't like the smell and don't eat your wool. I remember my mother had a wool sweater. They ate, and is she mad? And after that, we had a lot of mothballs. It has a characteristic smell to it. Now, let's talk about an interesting thing called graphite. How many of you have ever used a lead pencil? Guess what? Whether it's a number 2 wooden one or a mechanical pencil, like Dr. White uses. This one I've had around since 1980. I got about 8 of them. They no longer make it, and it's got a retractable tip. But anyways, the lead inside is not lead. They haven't used lead to write with since the early Roman days. What is lead? Well, that's an element, but lead pencils contain graphite. And these are large sheets of polycyclic aromatic 6-membered rings. And they're the lead and lead pencil. I've changed it. Huh. Give me 1 second. I took this one image I like to show off. The whole internet, that's weird, was on last semester. All right, let's use this one. Can everybody see the blue and white, blue and orange right here? Each one of those is a benzene ring or a polyatomic, and they're sheets. Now, how does graphite work? There's sheets of 6-membered rings that go on for long, hundreds of thousands of them. And if you have sheets, just like sheets of paper, when you write, the bottom sheet comes right off. This way, when you pull it, it's strong, but the sheets are barely held together by what's called van der Waals weak forces, and you can pull them apart very easily. And that's how graphite works. The next time you're using a lead pencil, you're leaving sheets of a polyatomic molecules on the paper. But you didn't think that was organic chemistry. It is. Now, one of the things, and let me just grab a sheet of paper here, is sheets of paper layered on top of each other. Each individual sheet is called graphene. And for many, many eons, organic chemists or chemists in general said, you can't just separate one and have it alone in a solution. And about 15, 20 years ago, now it's been a while, these two very creative chemists came along and did what's called the next grade crystallographer's trick. They took a piece of graphite, that gray stuff, a lump like coal, but it's not coal, and took some Scotch tape, stuck it on the top, and very carefully pulled it off, dissolved the back of the Scotch tape, and guess what you had? Sheets of graphene, which are very important discovery. They won the Nobel Prize for that. Now, graphene has very special chemical properties. And one of them is it's very light. And when you have it dissolved on things, it's very strong. And that is being investigated to this day. Now, another, and again, the switch is off. Let's talk about nanotubes. Back about 1995, give or take a year, both in Japan and in Texas, two independent chemists in Smalley in Texas, and I can't remember, I apologize to him, even though I've never met him, a Japanese researcher independently found that if you took graphite and reacted it in other carbon compounds, you could make tubes where you took the graphene to make tubes. Those look like good tubes, sorry about that. But these are tubes, and they're called nanotubes. Nano is the prefix 1 billion, and they're very tiny tubes, much smaller than I can show. And they have amazing strength, really strong, but they're lightweight. If you could make things out of nanotubes, it would be extremely lightweight and very strong. What would you want to do? Well, a car, an airplane. Think of how you can improve the gas efficiency, the gas mileage. You'd bring it way down because it weighs less. And since about 1995, 96, when they discovered that, the major countries in the world have been pumping billions of dollars into research into nanotechnology because of the future, and they're still doing that to this day. Oh no, guess what? We finished chapter 4, aromatic compounds. I have now officially covered all the topics that will be on test number 1. Listen carefully. This Wednesday, I will go through the aromatic problem set. This Wednesday, I'll go through the aromatic problem set. And a week from today, I'm changing it slightly in the syllabus because I changed it that. I will give my world famous review. It's world famous if you buy that. Anyways, students really say it helps them review for test number 1. And then a week from this Wednesday, we'll have test number 1. All right. Well, that means it's new chapter time. Now, if you look in the syllabus, I have chapter, I think 5 or whatever, alkyl halides. That's just a dummy chapter I put in there because I found it's easier to talk about alkyl halides when we use them in reactions. What's an alkyl halide? I can briefly, and now anything I cover will not be on test 1, will be on test 2. I don't even have slides for this, but I just want to briefly mention it. And we'll talk about this throughout the semester. Alkyl halides are our group, something with carbons with a halogen. Remember, X can be fluorine, chlorine, bromine, or iodine. And you'll see during the semester, being able to use that, make that, allows you to do other reactions like you just saw with Friedel-Crafts Alkylation. And I'll teach you in other functional groups how to make those kind of molecules. But I do want to talk about 2 alkyl halides, which you should be familiar with. This is the common name, the IUPAC name. Remember, treat a halogen just like an alkyl group, or it's a substituent. This is called chloroform, the IUPAC name, which nobody ever uses. This is called the common name, is that alkyl halide. And if you follow the news or movies, one use of chloroform is to knock people out. Please don't try it. Now, another important chemical is this. Carbon tetrachloride. If you're around organic chemists, we'll just call it carbon tet. And the IUPAC name, and I better write it down here because I'll need more room. Well, 4 carbons or 4 chlorines is tetra. This is one of the rare times I'll use that. Remember, 2 is di, 3 is tri. Tetrachloro. Methane, which nobody ever calls this. Now, one of the interesting things when you replace, like in methane, the hydrogens with halogens, you make it much less flammable. And back in the 1900s, 1901, or they were actually selling products that had glass balls filled with carbon tetrachloride as fire extinguishers. And this doesn't burn that easily. It will put out a fire. There's a problem. When you start putting halogens like chlorine on in a molecule, you make it carcinogenic. Carbon tetrachloride is highly, so is chloroform somewhat, but carbon tetrachloride is highly carcinogenic. And therefore, you try not to use it whenever. And it's time for a public service announcement from me, Dr. White. If you're in looking for a new home, one of the first things I did when I looked for a new home like this one I did, I checked in a couple mile radius, was there ever an old dry cleaners there? Or you can also look online for EPA Superfund fund. And what do I mean by that? Why don't you want to buy a house or a home where there was an old dry cleaning establishment? Because back in the 50s and 60s, Dry cleaning uses something else besides water to clean your clothes. Instead of in your washing machine, you have water, you have an organic solvent. And for many years, they used carbon tetrachloride. And it worked. But you couldn't dump it down the drain. And when it got dirty, what did some of the less scrupulous owners do? They'd take it and go across the street or half a block away to empty field and dump it. Well, now throughout Chicagoland, I think there are about 400 or 500 sites that are contaminated with carbon tetrachloride. I don't know, and they're quite hazardous. I don't know how many the EPA has cleaned up. For a while, they weren't moving on it. I don't know, I haven't really paid attention. But if you're looking for a new home, make sure check, and you can usually check the records or try Google to see if there was ever a dry cleaner there. And carbon tetrachloride is a liquid at room temperature. And for a while, it was also used in paints, and other organic halogenated compounds were used in paints, which was not good either, caused cancer. All right. That's all I want to talk about now about alkyl halides. And it's new chapter time again. So I get to do this. New chapter time. Now, this new chapter is going to be exciting. Plus, you got to be careful with some of the stuff I'm going to talk about. And this new chapter is alcohols. How many of you have heard the term alcohol before? I think all of you should have. Oh, before I do that, I forgot to ask something. How many of you happen to drive by a gas station and think, ooh, half the weight of gasoline is an alkane? Do you happen to turn on your natural gas to cook something on your stove or oven and think about natural gas as an alkane? Did you do? Uh-oh. Did you happen to light a candle or use baby oil or Vaseline and think those are alkanes? Remember, when you leave my class, you can still think about organic chemistry, because alkanes and organic chemistry is all around you. And you don't want me going, oi, you didn't do it. Come on, it won't hurt. All right, let's talk about alcohols. And again, this will not be on test 1. It will be on test number 2. And this chapter talks about alcohols, phenols. I know some of you call that phenol. It's really pronounced phenol, even though I've had arguments with chemists for eons in the United States how to pronounce it, and thiols. So we'll talk about stuff that are useful, that you got to be careful after you drink it, that you don't drive. And later in the chapter, I'm going to talk about something that stinks, really stinky stuff. So we got a lot to go through. All right, what's an alcohol? The general formula for an alcohol is carbon in a molecule with an OH group, also called hydroxyl group. I'll never ask you on test what a hydroxyl group is, but sometimes I'll say OH and sometimes I'll say hydroxyl group. The same thing, interchangeable. When you have this, you have an alcohol. Now in this chapter, what I'm going to do is show you some alcohols. We'll go through the general nomenclature, how to name them. Then I'll talk about something important in alcohols, general common names, and then I'll talk about where do you find alcohols in your daily life, which should be interesting. Well, I better get to work. And an OH group hydroxyl group counts as one bond to carbon. And once again, I do this instinctively, but I'll say it over and over again because it's important. When you look at an organic molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. Or like this. But anyways, I better not do that. You'll have whistle overload. Oh, an oxygen. It's got a hydrogen, hydroxyl group. It's on a carbon. Whoops, that I didn't want to do. My big fingers touch my pen, has buttons on it, which I don't use. And if you have a hydroxyl group on carbons, we call that an alcohol. So look for what's different. Hydroxyl group on carbon is an alcohol. So this is an alcohol. And the question is, how do you name it? Well, let's take a look at the rules. And this is IUPAC. The hydroxyl group OH in alcohol is indicated by changing the ANE ending of the longest chain contained with the hydroxyl group to an ANOL ending. So you drop the E at the end of the name of the longest chain alkane name and replace it with OL. That's how you indicate alcohol. Now, use a number to denote the carbon that the hydroxyl group is on, and this is for acyclic. In other words, not for rings. And good news, the rest of the IUPAC rules are followed, except the hydroxyl group has priority in the numbering system, meaning if you have a choice, that should get lower number than alkyl groups. Now, one of the things I will do this semester until the very end, when we'll deal mainly with common names, can you have a double bond and an alcohol in the same molecule? And the answer is yes. And IUPAC has rules for which functional group has priority over others. Do I know them? Yep. Am I going to teach them to you? Nope, because I'm going to keep it simple for you. Thank you, Dr. White. And for most of the semester, keep like alcohols just with alcohols. So let's take a look at how we do this. Now, if you look at the molecule I have, what's the longest chain with the carbon of the hydroxyl, with the hydroxyl group on it? And the answer is 4. 4 carbons, hopefully you learned that, is butane. But I have an alcohol, so I'm going to drop the E at the end of butane and change it to OL, butanol. Now, I'm not done. What carbon has the hydroxyl group? And you count from the side that gives that carbon the lowest number. 1, 2 from this side. 1, 2, 3 from the other, which is a lower number. Hopefully I'll pick 2. Isn't the math hard in my class? And this would be 2-butanol. Now, any alkyl groups on there, you would name just like you do alkyl groups on other alkanes. So let me give you one to try. And the question is, give the IUPAC name for the following molecule. Look for what's different. And when you're done, you know the sign. All right, I think everybody's done, so I better get to work. All right, what's different? Ooh, oxygen. Look for what's not carbon or hydrogen. Oxygen with an H on a carbon, that's an alcohol. Find the longest chain with the hydroxyl group, 1, 2, 3, 4, 5, 6. That's hexane. For an alcohol, drop the E, add OL, hexanol. For acyclic, not in a ring, what carbon is it on? 1, 2, 3. If I go the other way, 1, 2, 3, 4. What's the smaller number? Hopefully all pick 3. So that would be 3-hexanol. And let's do another one. And remember, it's your solemn responsibility. One of your colleagues did do today, and I thank them again. Remember, if I make a mistake with number of hydrogens, correct me. And the question is, what's the IUPAC name for the following molecule? And while you're doing that, don't forget tonight from 5 to 6:15, I have my office hours. If you need any help with anything, stop by. Don't forget, the link for that is both in the syllabus and also on the homepage of Chem 170. I see a couple people are done. Everybody done? I think so. Let me check. Yep, I better get to work. Now, what's different? Ooh, oxygen. What's not carbon? What's not hydrogen? Oxygen with a hydrogen on it to a carbon. What is that? Alcohol. If I can spell it right. And how do you find the longest name to name it? Name it as an alkane, the longest chain with the hydroxyl group on that carbon. Drop the E, replace it with OL, and if it says cyclic, plus the number. So here's my carbon with the hydroxyl group, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So longest chain is 6, and that's hexane. It's an alcohol, drop the E, add OL, hexanol. And notice this is carbon 2. If I went the other way, 1, 2, 3, 4, 5, and 2 is smaller than 5, so it's 2-hexanol. And look, oh, it's your old friend, the methyl group. And what carbon is it on? If this is 2, that's 4. So it's 4-methyl-2-hexanol. And that's how you do it. If I look at the clock, my goodness, time flies when you're having fun with alcohol. Ooh, bad doctor. But anyways, let's take a 5-minute break, come back at 2:50, and we'll continue. I'm going to get up and stretch again. Time to get started. All right, we were going through, hold on. That's better. I can see all right. We're going through nomenclature of alcohols. Let's do one more, or a couple more. And the question would be, and let me make sure you can see it. Give the IUPAC name for the following molecule, 3 points each. I have to ask, and I apologize for asking. Calvin, does my voice sound any better with your nice earphones?
Oh, absolutely.
Oh, really? Stick around after class. I'll talk about I have two actually, Cost Pro 4 AAAs. Have you ever heard of those headphones?
I don't think so, no.
They use them in recording studios for many, many years. All right, let's get to work. Back to chemistry. All right, if I look at this molecule, I look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen, and immediately I see an oxygen with a hydrogen on it, hydroxyl group, and it's on a carbon, so I now know I have an alcohol. And remember, find the longest chain, name it as an alkane, drop the E, replace it with OL, and if it's acyclic, not a ring, you need a number. And that number gets highest priority. So what's the longest chain? 1, 2, 3, 4, 5, 6. That's one chain. Remember, the chain has to contain the carbon with the hydroxyl group. And the other one would be 1, 2, 3, 4, 5, 6, 7, 8. Remember, this is how I write my sevens. And therefore, the longest chain is 8. That's octane. Drop the E, add OL, octanol. What carbon is that hydroxyl group on? Well, if I go from this side, it's carbon 3. If I go the other way, 1, 2, 3, 4, 5, 6. And I think hold on one second. Well, let me do it again. Sorry about this. One of these days I'll figure out why when I'm using my board a lot, word goes bad on me. All right, we're back in business. Sorry about that. All right, so if I go that way, it's 3, go the other way, it's 1, 2, 3, 4, 5, 6. So it'd be 3-octanol. And then as soon as I say that, this is all spoken for. Oh, I've got something left over. 3 carbons to the center carbon. That's isopropyl. And what carbon is it on? It's on carbon 4. So this would be 4-isopropyl 3-octanol. Now let's look at rings. For rings, you name the ring as the base name and then drop the E, add OL. But on a ring with no other functional group, the carbon with the hydroxyl group will always be 1. And therefore, since everybody knows that, we know not to put the 1 there. Ring, cyclohexane, drop the E, add OL, cyclohexanol. Now, in a ring, this hydroxyl group will always be 1. If we look at this one, I'll do this one, then I'm going to let you have some fun. What do we have that's different? Hydroxyl group on a carbon, and it's a 5-membered ring. So it's cyclohexane, cyclopentane, sorry. It's an alcohol. And this case, cyclohexalkane, drop the E, add OL, and no number for a ring, because this is always going to be 1. But I'm not done. I have this, and that's on carbon 3, and that's 3, and you can put shirt, but I'm going to be a lazy organic chemist, 3-T-butyl cyclopentanol. And that's how you do rings. So it's time for me to let you have some fun. And why don't you give the IUPAC name for the following molecule? 3 points each. And in coming weeks, you'll see I spend less time on nomenclature. I'll be spending more time on reactions. Remember, this is for test 2, not test 1. I see the thumbs are up on a number of you, and others are still working, so please be patient. All right, I think everybody's done. Let's get going. What's different? Oxygen. on a carbon in a ring, that's an alcohol. Hydroxyl group on a carbon, alcohol. And you name the, in this case, ring, cycloalkane, drop the E, add OL, and no number for a ring. Because the hydroxyl group carbon is 1. Well, 6-membered ring, cyclo, don't forget the cyclo, hexane, drop the E, add OL, cyclohexanol, and then, oh, it's your old friend, the methyl group, and it's on carbon 2, so that will be 2-methyl cyclohexanol. Now, there are 2 types of nomenclature skills you should have in organic chemistry, which means there are 2 types of nomenclature questions I can ask you. One is, here's the molecule, give the IUPAC name. The other is, here's the name, draw the molecule. So let's take a look. At the following. And the question is, how do you decode this to know what to draw? Well, you start at the right and you move left. OL ending, alcohol. If this were an E, no name is 9 carbons. So I better get to work. I have 9 carbons. Now, something I shouldn't, personal thing about Dr. White. When I learned organic chemistry as an undergrad, my instructor always started numbering alcohols and other molecules of oxygen from the right. And I still do that. Good habits I don't break. But if you want to do it from the left, you can. But I'm going to do it from the right. So that's 1, 2. The 1 here tells me the hydroxyl group is on carbon 1. Then I have a methyl group on carbon 3. And now I have to put in my hydrogens because you know there's 4 bonds to carbon. And if I made a mistake, please let me know. I don't think I did. And that's how you do it. Remember, you start from the right, move left, and OL ending is alcohol. And so it's time for me to give you have some fun. And here's one, 4,5 dimethyl. Remember, di means 2, tri means 3, dimethyl 2-decanol. Draw the structure for that, please. While you're doing that, I need a new water bottle. Mine's empty. I'll be right back. If we had been in our classroom, right outside our classroom at ECC, the chemistry building, there's a water fountain. I would have gone out and filled my water bottle, but since I'm at home, I have 3 more of these, now 2 in my refrigerator, ready to go. All right, everybody done? All right, I assume everybody's done. I better get to work. How do you do this? You start from the end, the right, and move left, OL ending. OL ending, alcohol. If that were E decane, 10 carbons. And where's the hydroxyl group of the alcohol and carbon 2? And methyl, CH3, di means 2. Where are they? On carbons 4 and 5. And now I know there are 4 bonds to carbon. And there you have it. 4, 5, dimethyl, 2, decanol. Oh, let's do one more. And that would be 4-T-butyl cyclohexanol. Draw the structure for that molecule. Thank you, Joe. And you too, Calvin and Emily. And Cam. And I think Megan's done too. So let's get to work. I start from the right, move left, OL ending, alcohol. Remember, hydroxyl group on a carbon. And if this were an E cyclohexane, I have a 6-membered ring. And it has a hydroxyl group. This is 1. I have a T-butyl on carbon 4. So you go clockwise or counterclockwise. Carbon 4 is here. And I'm done. At least with that structure. Now, there's one special alcohol I'd like to talk about, and that's this one. When you have a benzene ring with a hydroxyl group, no, it's not called benzol. This molecule has been named eons ago. It's called phenol. Now, you probably know it as phenol. I worked for a company and we used to use railroad cars worth every week, lots of it. I had a running argument with the chemists in the United States. I call it phenol, they call it phenol, and we still have, when I left, had that argument. But I'll call it phenol if you want to call it phenol. Good news, I'm not giving verbal quizzes, enunciation quizzes. I knew one instructor who did. I don't. All right, now, this is called phenol, and this is all both the what's called the common name and the IUPAC name. And you should know that. If I ask on a test, what's the name of this phenol? If I ask you to draw it, that's what it is. And how it got that name, I sort of have an inkling, but anyways. Now, I won't put on tests, but they're named the same way as toluene with the methyl group. So I could have something like, oh, I'll write it over here. And orthoethyl phenol, which I won't put on test. Phenol, don't forget the lines for the benzene ring. And ortho is 1,2 disubstituted. And that would be how you do it. Well, I'm not going to put that on the test. Now, I should mention I'm a world authority on phenol and its reactions. My last US patent dealt with my knowledge of phenol and other chemicals. And their name are named with the hydrox group on the benzene and the phenol name. All right. All right, I don't have a slide for it. I thought I did. I skipped the slide, that's why. Doesn't matter. Let's talk about common names. And common names are names of alcohols that have been around for centuries, long before they were used by IUPAC. And the common name for alcohol is derived by naming the chain the hydroxyl group is on as an alkyl group, and then adding the word alcohol at the end. C-board for ethyl alcohol, isopropyl, and tert-butyl or T-butyl alcohol. I better get to work. And in real life, we are face to face. You'd be watching me, just like you are now, draw this on the whiteboard. And you see my lines are not that straighter on a whiteboard than I am on my tablet. Now, this molecule here is quite an interesting molecule. And since you can only have the hydrox group on one carbon, you can't have two, ethane, drop the E, and this is ethanol. Now, if I were to hide this from you, you'd say, oh, this group is an ethyl group. Now, switches on for this chart, and let me explain. On my test, and the final too, on my test, and don't forget, this is test number 2 material, I will never ask what's the common name of that molecule, but I will ask you to draw the structure of the molecule with the following IUPAC or common name. Why am I doing that? Because to this day, a lot of things you'll find the IUPAC or common name on a label as opposed to IUPAC. Now, ethanol, and it's not one ethanol, because it's impossible to have two ethanol, because the carbon with the hydroxy group is always going to be one. This is the one exception to acyclic alcohols, where you need a number, and ethanol was also known as ethyl alcohol. Now, if you look at wine bottles, you'll see ethyl alcohol. If you look at other things, like next time you're in a gas station, ethanol. Now, ethanol is used as gasoline, but it's also the small little molecule, only two carbons, and a hydroxyl group and hydrogens, that's found in beer, wine, and hard spirits. You know, the good stuff in like Canadian Club, Absolute vodka, Grey Goose vodka, Dr. White likes vodka. And by the way, quick tip, if you're a vodka drinker, go to Costco if you have a membership and get their more expensive, what they call French vodka. And it's almost that close in taste to Grey Goose and Absolute. It's a lot cheaper. Don't get their super cheap American. Now, quick thing, if you buy what would be inexpensive alcohol, hard liquor, and you wake up with a hangover, that's because there's certain phenolic compounds that are in there, not in the expensive stuff, and that gives you the hangover. If you drink high quality alcohol, and I'm not saying you should, especially if you're under 21 in the state of Illinois, you won't get as bad a hangover. As my father once taught me years ago, don't mix liquors. If you're doing vodka, stay with that the whole night. But anyways, that's ethyl alcohol. Let's go to the next one. We have this longest chain, 1, 2, 3, propane. Alcohol, propanol, the hydroxy group, that's 2-propanol. Nobody calls it that. What they do call it is, what's this group here? Isopropyl. And ending alcohol, and that's isopropyl alcohol. And where can you find it? Well, if you go to your local big box store like Walmart, 70% isopropyl alcohol. I could spell it. And 30% water, homogeneous solution, and we call that rubbing alcohol. And about 8-10 years ago, they started making rubbing alcohol. You can also buy up to 90% isopropyl alcohol and 10% water. And that's a very good disinfectant. Do I have time? Oh, I do have time. Now, most of you are probably grew up with the electronic thermometer when you go to a doctor's office. How many of you remember the mercury thermometer they put under your tongue and you had to wait 3 minutes? Nope, generation. Oh, one person does. If you ever go in a doctor's office when I was young, you'd see this sort of like V-shaped circular container that had rubbing alcohol, and sometimes they were more cylindrical too, and the room's thermometer. And the nurse would take it out, wipe it with a cotton ball, and stick it under your tongue. And if she didn't wipe all the alcohol, rubbing alcohol, it tasted bad. I still remember it tasted bad. And why did they have that? Isopropyl alcohol and water, rubbing alcohol? Because it kills germs and microbes. And to this day, it kills COVID-19 germs. I don't know if you call them germs. Well, viruses, that's the right term I was searching for. Also, ethanol will do that. How many of you have seen that stuff you can buy hand cleanser that's just a liquid, and it's sort of a gel, really. And that's water and mostly alcohol, ethyl alcohol, and that will kill germs and also viruses too. Now, when they first started selling that, I went to my local bank long before COVID-19. I saw they had these big bottles of that there. And the teller who was taking care of me, knows me quite well, and said, "Could you bring that bottle over?" And she did. I say, "See what it says in the back?" It was like something like 162% or higher ethyl alcohol. I said, "That's flammable. Make sure nobody smokes or lights any cigarettes around it. You'll have a fire." And it's true, you will. Now, the last one, if we look at this molecule, the way I have it written this way, longest chain, 1, 2, 3. That's propane. The hydroxyl group is on carbon 2. So it's 2 propanol. I also have a methyl group on there. And it's 2-methyl, 2-propanol. But if I rotate this molecule 90 degrees, it looks like this. And what group do I have here? It's one of Dr. White's favorites. It's a T-butyl group. And nobody calls this molecule 2-methyl, 2-propanol. They call it T-butyl alcohol. And I've worked with it. And if we were doing a lab face-to-face, we would work with that. Remember, common names, I will give you the name and ask you to draw the structure. I will never give you the structure and ask for the common name. And that's because you'll find it on labels. Speaking about labels, we're talking about phenol, and it's show and tell time. How many of you are familiar with this product? Not that I get any money back from them. Oh, product placement. Can I get one? No, I don't. And if you look at it, and I love this in the winter, you put it on your lips so they don't get chapped in the real cold of winter when you go out. And one of the key ingredients is phenol. And this is the phenols in there. And that also has antiseptic properties. If you ever put this on, you feel that tingling on your lips? That's because the phenol is doing that. All right, we talked about phenol. All right, next couple of slides, it's important for me to discuss this, but click, I'm turning the switch. Will this be on a test in the off position? And let's talk about hydrogen bonding of alcohols. What's a hydrogen bond? In case you forgot from general chemistry, it's a weak intermolecular. Inter means between two molecules attraction between the non-bonding electrons on nitrogen, oxygen, or fluorine, and a hydrogen atom, which is bonded to that atom. And it's weaker than a regular covalent chemical bond, a single bond, but it has significant strength properties and affects the physical properties such as the boiling point and solubility of what we call polar solvents. Alcohol is one, and water. And alcohol can hydrogen bond with each other and water. And what does that mean? Let's take a quick look. Again, switches off. If I have any alcohol, because of the difference in electronegativities, hydrogen has a weak strength to hold the pair of electrons in this bond to it. So there's a slight positive charge here, and the oxygen, there's a slight negative charge. And if I have another alcohol, let me Draw it a little lower. Same thing. And there's a very weak attraction between the negative charge, and this is lowercase delta, which means small difference. Capital delta means difference. And this is called the hydrogen bond. And it's a very important force. That's why alcohols are liquid at room temperature and not a gas. Also, same thing's true. Water can hydrogen bond. Again, hydrogen bond. And that weak attraction also makes water a liquid at room temperature, where you'd expect it to be a gas. And think about how life would evolve on our planet if water was a gas. Your blood wouldn't be in your veins the way it is now, because it would be a gas, not a liquid. Our life would be looking different, I would think, but I'll let you ponder on that. So alcohols that can hydrogen bond like that and because of that, they can, one, be a liquid at room temperature and have higher boiling points. And two, smaller alcohols are soluble in water. Oh, a message from Dr. White. Do not tell bartenders, you know, you can make alcoholic drinks because alcohol can hydrogen bond to the water and makes it more soluble. Bartenders do not like to be taught organic chemistry. Trust me, I found that out firsthand years ago. Now, switch is still off. Let's talk about the acidity of alcohols and phenols. Now, alcohols are very weak acids, but their conjugate bases are strong bases, and I'll explain that in a second. Now, alcohol is a weak acid, but it's much more stronger acid than alcohols. And this is due to resonance stability of what we call the phenoxide anion, which I am a world authority at Seaboard. And maybe in other classes, you may need to understand this, but what's an acid? A proton donor. And there's an acid-base equilibrium. And if it's an acid, it gives up a proton. And notice the equilibrium is very small this side and mainly here. This is a weak acid. Actually, it's a very weak acid. But its conjugate base, which I'll teach you later, is called an alkoxide, is a very strong base, much stronger than sodium hydroxide. Again, I can't spell, but I was always first one down in spelling bee. Now, when we talk about phenol, and now Dr. White's going to have some fun. Now the equilibrium is much more to the right. This is called the phenoxide anion, which I used in my last patent. And why is this a stronger acid? It's just a weak acid, not a very weak acid. Because the more resonance forms you can draw of something, the better it is. And another resonance form that I could draw, and you don't have to write this down, and I could do two more. And because when you can draw resonance forms, you make it more stable, this is more likely to go to this way because this is more stable than this because you can't draw resonance forms. Again, switch was totally off on this slide, but still important concept you should be aware of. Now, alcohols can be bases. And what is a base? Something that accepts H plus or a proton. Switch is clicked totally off on this slide. And this is the first step in two important reactions of alcohols. Really? Yep. And again, switch is off. But let's look at something. A base, if this is going to be a base, here I have an acid, and it reacts to form this. Does anybody see anything interesting in that new molecule I just drew? Let me write the hydrogen better. Two hydrogens and an oxygen. Two hydrogens and an oxygen. H2, and it's water. And this is an important step in some reactions with alcohols. You first react with acid, and when you have a good leaving group, it does. And this is called the carbonium ion. Switches off on this slide. And these are extremely reactive. The newer name, which I hate with a passion, called carbocation, I don't use. And these are very reactive. I mean, very reactive species. And I'll be teaching you more about using acid and other things to make new molecules. Now, how do you make an alcohol? And I should point out, now that we've learned enough general reactions, coming chapters and new functional groups, I'll introduce you. I forgot to introduce you to one thing. I'll introduce you to something. Hello, this is an alcohol. We'll go through some of the nomenclature for both IUPAC and common. I've talked a little about some of the uses, ethanol in gasoline, and also hard spirits, which you shouldn't drink unless you're of age. Dr. White still likes his vodka and Canadian Club. And also isopropyl alcohol and rubbing alcohol. There's one alcohol I forgot to talk about, so I better do it real quick. How many of you have ever gone to the dentist and before they inject you with the Novocaine or whatever they're going to do to deaden the nerve? Unfortunately, in my family, it's hereditary. Lots of dental problems, which unfortunately I inherited from my mother, so did my sisters. And if you go to a good dentist, before they inject you, ouch, they'll rub something right on the surface of your gums. So when they put the needle in, it doesn't hurt, which is being a good dentist. You don't feel anything. What do they put on there? It's called Eugenol. And notice this molecule here has a hydroxy group on the carbon benzene ring. It's a phenolic compound, really an alcohol. It has another functional group, also a double bond. And where do we get this from? Cloves. This is oil of cloves. Whenever I smell cloves, Unfortunately, I think of a dentist's office. This won't be on test, but the next time you smell cloves, if you have it in your house, like you put on your ham for the holidays, a lot of people do. Think about it, you're smelling an alcohol. Not the kind that will get you inebriated, but it is. Now, how do you make an alcohol? Well, this is the only reaction that can be on test 1 and test 2. My test, I just keep the reactions to what's the concepts or functional groups I talk about. I don't go back and do earlier ones because that's not fun. But this is the one where I can talk about, take a double bond, react it with acid and water, you break the pi bond, and one carbon gets H, the other gets OH, and I don't have it here, but I can write it, and it follows Markov-Nikov's rule. And since we've gone through this, I can let you try out an example. I'll do one. I'll do one real quick. And what do we have here that's different? Double bond, reacting it with acid. Remember, H plus is an acid, like sulfuric acid, H2SO4, and water, think of it as H, OH, hydroxyl group. You break the pi bond, one carbon gets H, the other gets OH, the hydroxyl group, and it follows Markov-Nikov's rule. The carbon with the most hydrogen gets the hydrogen, the other carbon gets the hydroxyl group. This has 2, this has 1. Do you break carbon-carbon single bonds? No. So the hydrogen will go here to 2. Hydroxyl group will go here. I'll put in my hydrogens. And now you know I've made an alcohol. And that's one way of making alcohols. There are a couple others, but I'll teach you that later in the semester. Your turn. Give the organic product or products you're following. Hurry up, we're almost done. Oh, you got a minute or so to take your time. Uh-oh, I'm seeing all the thumbs come up. You know what that means? You guys are learning organic chemistry. Thank you. You've made Dr. White happy. All right, I think everybody's done. Let's do it. What's different? What's not a carbon-carbon single? Oh, double bond. Reacting with acid, H plus, water. Remember, water is H, OH. You break the pi bond. One carbon gets H, the other gets the hydroxyl group, OH, and it follows Markov-Nikov's rule. The carbon with the most hydrogen gets the hydrogen, the other carbon gets the hydroxyl group. If I look up here, here are my 2 carbons, double bond, 2 hydrogens, oh, 0 hydrogen. Hopefully I'll pick 2 as greater. I don't break my carbon-carbon single bonds. This carbon had 2, so I'll get the hydrogen. The other carbon will get the hydroxyl group. I know there's 4 bonds to carbon. And I'm done. I've just made T-butyl alcohol. And if I look at the clock, I am done. Wow, time flies when you're having fun with alcohol. Oops. I shouldn't have said that. But anyways, don't forget, do the lab. I know 4 of you have already handed it in. Don't forget to hand your lab if you haven't. Don't forget to hand in, if you haven't, your signature sheet in the assignment area, black D2L. And don't forget, tonight I have my office hours from 5 to 6:15. If that's not a convenient time, send me an email. Maybe I can switch it to another time. It's more convenient for everybody. With that, don't forget, wear your mask. If you haven't been got your vaccine injection, get that. And I'm going to say, gang gesund. Bye. I'm done.